So it says let f of x be equal to that 3e to the 2x, and g of x is 6x to the third. Where does it have parallel tangent lines? So when you see parallel tangent lines, what I want you to think of is the same slope. Okay, so where are these the same slope, or their slopes are equal? Okay, now it's a tangent line. That means a tangent line is based off one point. So that means it's the slope of a tangent line, which again is the definition of derivative. So we're essentially looking for where is the derivative of f equal to the derivative of g? What x value? Okay. So to do this, let's find all these derivatives. So the derivative of f prime, so we're doing the derivative of this thing right here. You're going to need to know the exponential rule for derivatives as well as chain rule, because the 2x is inside of that function. Okay, it's e to the 2x. The outside layer would be the e, because if you knew what x was, the order of operations would be 2x. That's the first thing you do, so that's the innermost function. The outermost is the e. So we're going to do 3e to the 2x, because the derivative of e is itself. And then you have to multiply by the inner derivative. In this case, it'd be 2x. The derivative of 2x is 2. Okay. This is going to be equal to g prime, which is just straight up power rule, so it's 18x squared. Okay. Now, if you wanted to, you could simplify this. It doesn't really matter if you do that or not. The main thing that you should see on this is you cannot solve for this algebraically. The best you can do is guess and check. Okay, there is no way to isolate x. It's all over the place. So when this happens, the easiest thing you can do to solve this, well, there's multiple ways of doing it. The fastest way would be just to check every single one of these values and throw it in for x and see which one of them makes both of them the same. Okay, that works for multiple choice though. It doesn't work for every problem. It's better to learn how to solve every problem. That way you can still solve the multiple choice as well, because it's part of that, that Venn diagram of any problem. So what I would want you to do, ideally, again, just in case this is free response, is to figure out how to figure out what x is here using a graph. So we're going to graph one, we're going to graph the other, and we're going to figure out where they intersect. So it's kind of like old school algebra 1 when you found intersections for like systems of equations and stuff like that. That's what we're going to do with these two equations. Where are these two equations equal? Well, let's graph it and try to figure it out. Okay, so I highly advise doing it this way, because again, if it's free response, it's the only way you're going to be able to solve this. Okay, so please follow along with what I'm doing here. In your y equals, we're going to put in the, 6e to the 2x. Okay, the other one, it's going to be 18x squared. I'm going to turn off this second derivative thing right here, because all we need to do is figure out where these two meet. Zoom 6 is your friend. AP always puts problems where it's basically on Zoom 6. You don't need the Zoom standard is what Zoom 6 is. If you click Zoom, the 6th one is Zoom standard. A lot of the times, that's all you need. It's not like where you have to hunt where the graph has both of them being equal. If that ever does happen, though, just hit Zoom 0, and it fits both of them to the screen. Never mind, don't do that. That does not help. I would have to zoom out to see that. It's kind of annoying. Anyway, the intersection that we're looking for is right there. And if you do not know how to do this, make sure you pay attention, because this is muy importante. You hit second calc intersect, so second calc 5, and then it says first curve. I want the blue curve to be my first curve. The red curve is my second curve, and then you just hit enter. For guess, if there are multiple intersections, which does happen sometimes, and you want to find one intersection specifically, you have to move that cursor closer to that intersection point. Okay, this one, it doesn't matter because there's only one. I can move that cursor wherever I want. It will still find the intersection. But the guess, you have to move that cursor closer to wherever it is. Now, what the calculator is actually doing behind the scenes, if you know anything about for loops from coding, it's literally just looping through every single possible number and trying to find one that's equal to that. Okay, it's actually probably using a binary search, but that doesn't really matter. All you need to know is this calculator is doing guess and check super fast. So when you hit enter, it guess and check that quickly to find it. Okay, and you could have done that yourself. You could have plugged in 1 and been like, whoa, 1 is way off. Okay, let's try 0. Oh, 0 is way off. Let's try -1. Oh, -1's way off, but it's in between. And then just keep trying more and more numbers. It would just take you a year to do that. Okay, the calculator can do it super fast. And if you notice that x value at the bottom is what our answer is. So what I'm going to do is screenshot this just so I can write on it. Again, make sure you know how to find intersections on your calculator. You will absolutely need it for this class. Okay, if I zoom in right here, that's where the intersection point is. It says, what's the value of x? The value of x is right there. And you can even test it out yourself by plugging in x to both of these. You'll see that they're both equal. So the x is approximately, whoops, that's embarrassing, approximately equal to negative 3.91. Okay, you do have to round to 3 decimal places unless it says otherwise. This one gives you the answers as 3 decimal places. So the answer is C. Are there any questions on what I did there? What's that? Sorry.
Yeah. Why is the parallel? That's where that is supposed to be.
Oh, great question. Oh my gosh, that's such a great question. This is so many levels on that question. Very good. I should have thought of that ahead of time. Check this out. I graphed the derivative, so it's hard to tell the tangent lines, but watch this. If I do f of x is equal to, what was it, 3e to the 2x, and then g of x was equal to 6x to the third. If you look at these, this is going to be kind of hard to find. If you look at these, we're looking for where is the tangent line equal. So if I need to write on this, so that's why I'm doing the screenshot. All right, so it's like negative 3.91 or something like that. This is going to be semi-hard to find. This is just estimating based on looking at it. But like negative 0.5 is like maybe right here. Negative 0.39 is like, I don't know, this way a little bit. And if you try to draw a tangent line for it, for each of those, it's going to be about the same. Again, it's so rudimentary on kind of how I did it there. But does that make sense? But you graph the derivative to see where they're equal. So you graph the slopes of those lines that I just drew there. Not the little 0.5 marker, but that's essentially where the slopes are equal. And it looks like it could be equal in other places, but it's really, if you zoomed in, you probably wouldn't be able to see it that way. Okay, so what I'm going to try to do is local linearization on this. Here, let's do this. X is equal to negative 0.391. Here, hold on, let's set this equal to A, and then we're gonna graph A, f of A, oops, that's embarrassing, and then A, g of A. Okay, so I was off because I thought that was a 1 there. But essentially, hold on, let's cram these down right next to each other. Essentially, if I zoom in here, these should be the same slope. I'm going to try to cram this down a little bit more. Hold on. This is getting crazy. But you'll notice those slopes are the same. Local linearization, remember, if you zoom in, it becomes lines. And if I did this better, I don't know. Ah, man, I'm sorry. I should just find the equation of the tangent line and draw each of those in there. This is a little bit better. You see other parallel? Very good question. Very good question on that. It's hard to see though because I graphed the rates and found the intersection with the rates rather than the originals. These are the original equations. Original is not a math term, by the way. You would just say f of x, you would rather than f prime. When I say original, it means without the prime. It's just f by itself. Okay. Now let's go a little bit deeper into this. Let's do f prime of A and g prime of A. You'll notice they're about the same. I rounded to, really the decimal place goes forever, but you can see those are pretty darn close. And if I made an equation of a tangent line, you'd be able to see it a little bit more too.